Okay, so let me start by thanking the organizers for this event. So I'll be talking about testing the area theorem with GW observations, and this work is being done with Prayush and Ashwin, who is a visiting student with Prayush. So this is going to be the outline. So first of all, I'll give what exactly the problem statement is. Then we will see, since we'll be working in a time domain framework, I'll explain what exactly a Bayesian analysis means in time domain. I'll just write down the formula for likelihood. And once we have the likelihood, then we can estimate the in-spiral and ring-down parameters, and which we will require for testing the area law. And then we will see whether the area increases in a binary black hole merger process. Okay. So Hawking area theorem states that in classical GR, the total surface area of a black hole event horizon in a closed system can never decrease over time. It can remains constant or it can increase depending on what type of configuration you have. If you have a static space-time or stationary space-time that has a killing time-like killing vector, it will always remain constant. But if you are perturbing it with some external energy momentum tensor, it will always increase. So how to test it? So theoretically, it is very easy. So if you have, let's say, a field equation which is of this form, you don't even have to assume GR. So let's say if you have a field equation GAB plus HAB is 8 pi TAB, where HAB is, let's say, the correction over GR. Then you can write down the area element of the codimension 2 surface, which we call the horizon, and take the variation of the area. And after doing some computation, you can show that it's proportional to theta square plus sigma square term, which are positive definite. And theta and sigma are expansion and shear of the horizon. And there is a term which will be proportional to GAB plus HAB, KAKB, where K is the horizon generating null vector. Now, if you are in GR, that means HAB equal to 0, provided that null energy condition holds, you can see that delta A is always greater than 0. So it's very easy to see in GR how area increases. In any modified theory of gravity, you have to, of course, see what exactly the functional form of HAB. It will depend on the kind of theory you are considering. So this is what you can do theoretically. How do you test it observationally? So the detection of gravitational wave actually provides us a very nice framework to test not only this area, but any strong field test of GR in general. So here is a cartoon for a typical binary black hole merger that we see at LIGO. So initially you have an in-spiral phase where you have two curved black holes far separated from each other. They merge and finally form a final remnant after radiating some energy in the form of gravitational waves. So if the area theorem is a fundamental property of black holes in GR, it would be reasonable to anticipate that the area of final remnant formed after the merger should exceed the sum of the initial inspiraling black holes. So that will be the whole idea here. So we will be finding the ring down parameters from the ring down phase of the signal. There is a final mass and final spin, and initial parameters, that is M1, M2, A1, A2, from the in-spiral part of the waveform independently. Then we will compute the area final and area initial, and we will see whether area increases in such a binary black hole merger process. So this is the methodology that we will follow. We will cut the signal at the peak of the waveform or even few seconds before it, so that we can isolate the in-spiral and ring down process, ring down space. Once we have isolated a ring down part, let's say, we will compare this. Of course, the ring down part will depend on the final mass and final spin, and the in-spiral part will depend on initial mass and initial spin. Of course, all these localization parameters. And the area is of this form. If you assume these are to be generated, this gravitational wave to be generated by some curved black hole, then this is the area formula. So once we have a estimate of M1, M2, A1, A2, and MFF, we have a direct computation of what exactly the area is. So since we will be performing, so here you can see that we will be cutting the signal at the time domain at some time where the signal is peaking or at the merger time. It's good to stick to a time domain analysis. So, but typical LIGO analysis involves parameter estimation in frequency domain. And the frequency domain likelihood is of this form. So here DI is the Fourier domain data, S is the Fourier domain signal, and S is the power spectral density, which is an estimate of the noise. So if you have data and model and some estimate of the noise, you can of course put this likelihood in a sampler, and that will give you the posterior distributions. But in frequency domain, the distinction between in-spiral and ring-down phase is a bit ambiguous. I mean, you can do it. Typical LIGO analysis in the context of IMR checks, IMR consistency checks, they cut the signal in frequency domain at the F ISCO, where ISCO frequency is the frequency of an particle in the innermost stable circular orbit. And that is a very good estimate. The ISCO frequency is actually a very good estimate where in-spiral phase will end. So you can do it in frequency domain as well, but a more rigorous approach would be to split the signal in time domain. So if you wish to do it in time domain, this is how the likelihood will look like. So you have time domain data, then you have Cij inverse, which is the noise covariance matrix, which is inverse Fourier transform of this PSD basically. So you see that in frequency domain, you have to process a one-dimensional area, the power spectral density. Whereas for the time domain analysis, you have to process a n cross n matrix at each likelihood computation. So it's just computationally more expensive. That's why LIGO analyses are mostly done in frequency domain. That's the only reason. So let's start with the ring down part. So ring down part is basically given by a damped sinusoid. If you start with, let's say, curved black hole, and if you perturb it with some spin-as perturbation, then this is what the perturbation equation will look like. So you can split in, separate the radial and angular part, where ALM is the separation constant and omega is a complex number that is called the quasi-normal frequency. And you can solve these two equations by imposing some boundary conditions, so-called the black hole boundary conditions, which is basically a purely ingoing wave at the horizon and outgoing wave at the infinity. So you have two equations and two unknown, this ALM and omega, and in principle, you should be able to solve it. And this is the most computationally expensive part or challenging part in the ring down analysis, because once you know this omega, computing this FLM and tau LM and the frequency and decay time is very straightforward. And once you compute the H and L, see this H plus and H cross, you can just project it to a detector, and that will be basically your S. That is your model. So now what remains is data. Data, of course, we can download from the LIGO site. So that the detector data for a given interval of time. So, and Cij, of course, you can estimate from the detector noise. So everything is there. So you can just put it on a sampler and it will give you the posterior. And yeah, so these are some results. So for GW 150914 and 190521, I have plotted here the mass final and spin final, where I have just taken the two to here, as you can see, it's a function of LMN. So I have modeled the, in principle, it will take all higher values of LMN as well, but just restricting to 2 to 0 and 2 to 1 mode is a very good estimate. So by doing that, I'm able to compute the final mass and final spins. Similarly, for the in-spiral part, so far we are doing it in frequency domain. So we have separated the signal in frequency domain at the F ISCO. And after that truncation point, before that truncation point, we will take it to the in-spiral model and compare it with various in-spiral phase of various gravitational wave events. And basically that will be your data. And your model is some, let's say, IMR phenomenological model. And with an estimate of PSD, you can again run a Bayesian analysis to compute the M1, M2, and A1, A2. And once you have the area final and area initial, then you can check that. For 150914, people have done already the test of area law. And as you can see here, they have plotted the delta A by A, where delta A is the area final minus area initial, and A0 is the initial area. And it's the claim is that it satisfies the area law for 90 with greater than 97% probability. So you can see that most of the region is always positive. But the point is that it is important to note that the analysis is limited to only one event. So it should not be called as a observational test of area law unless you test it on various other black hole events with a larger data sets or larger parameter space. So that's what we are doing here. So 2 minutes. Yeah. So that's what we have done here. So for example, for 190521 and 170814, here I have computed the area initial and area final Of course, the Ringdown parameter is estimated in time domain, and in-spiral parameter here is estimated in frequency domain, where f ISCO is the truncation point. And you can see that there is always a very small overlap between these two areas. So if you plot it, the change in area with respect to divided by the original initial area, you see that most of the time it is positive with a very small region in the negative part. So we have established that for most of the event that we have checked so far, it satisfies the area law with more than 95% of probability. For one or two event, I have some negative results, but I think I have to check some of my data analysis for that. I'm not sure much about those results. So here's the summary. So in this analysis, we are verifying the Hawking area theorem for various GW observations. And in particular, we are considering events that has sufficient SNR in the Ringdown phase, so that you can, or mostly events which has SNR greater than 7, so that only you can recover the Ringdown parameters. So yeah, so one of our immediate goal would be to do the in-spiral phase as well in time domain, which will be our next task to do. The frequency domain method was easier, so I started with that. But ultimately, we will do in time domain. And another future work that we are planning to do is that this is in the context of GR. But if you have a modified theory of gravity, the world entropy is not equal to the area of the horizon. That is true in GR, but not in a general theory of gravity. So the question is whether in those theories area increases or entropy increases. So those kind of things also we are looking at. Yeah, so I'll conclude with that. Thanks.
On to Q&A session. Any questions? Yes, Chandru.
The fact that you lose mass by gravitational rays, is that also being accounted?
Yes. Okay. So of course, mass is radiated. So the final mass is of course less than the sum of initial masses. So if you have a Schwarzschild black hole, for example, in that case, if this was the case, the area law will be violated because the area was 4 pi m square in Schwarzschild case. But here the area formula is a bit different. So even if your mass increases, the area will always increase. You can show that.
So there can be scenarios where since you are radiating gravitational waves out, there can be scenarios where the final mass need not be greater, right? Because some mass is always going out of the system. So
so final mass will always be less than the sum of initial masses. That is always true, but area final will always be greater than area initial. That's what we are saying. So area is not proportional to m square, or it's not a linear or quadratic relation, just as Schwarzschild case. So even if mass decreases from initial to final configuration, area always increases.
I have a question. So also, there's no problem with Schwarzschild also, right? You just get m final squared is greater than equal to m1 squared plus m2 squared.
Yeah, I think so.
There's no problem even then. But what I was asking is, when you combine the posteriors from the in-spiral merger part and the Ringdown part, I mean, do you do some sort of joint estimate of the posteriors on area? Because if I have say m1, m2, I get lower estimates. Correspondingly, I also get lower estimate for m final, say. But I also have some m final from higher m1, m2 parts of the posterior, right? But is it right to compare them directly? Because then your estimates are not point estimates, right? It's a posterior. Yeah, so how do you combine the posteriors? Compare the posteriors.
So both are independent so both parameters, the area initial and area final, are measured in completely independent way. So then I think there is nothing wrong to compare them.
Okay, I might follow up later. It's okay.
So we are out of time for this talk. Thank you very much for your wonderful talk.